projects. In this video, we are going to explain about the project entitled as Time Series Forecasting for Peak Hour Traffic Accidents. So before getting into the video, let me give you the brief explanation about the project. The project focuses on analyzing historical traffic accident data to identify patterns and trends related to peak hours. By applying time series forecasting techniques, the study aims to predict accident occurrence during high risk periods such as morning and evening rush hours. These predictions help traffic authorities take proactive measures to improve road safety and manage traffic more efficiently. Coming to the abstract explains the overall purpose, approach, and significance of the project in a cosine manner. It begins by identifying peak hour traffic accidents as a major problem in urban transportation, emphasizing the causes such as high vehicle density, driver stress, and limited road capacity. It then highlights the importance of accurate accident prediction, explaining how it can help reduce fatalities, injuries, and economic losses. The abstracts further describes the methodology, stating that historical traffic accident data is analyzed using time series forecasting techniques to identify temporal trends, seasonal variations, and recurring patterns. Models such as Arrhemia, S-Arrhemia, and deep learning based approaches are mentioned to show the analytic and predictive techniques used. Finally, the abstract outlines the outcome and impact of the project, explaining that the proposed system provides reliable predictions that help traffic authorities take preventive measures in advance, thereby improving intelligent traffic management and overall road safety. Coming to the existing system is mainly designed to analyze traffic accidents after they have already occurred using traditional statistical techniques and periodic reporting methods. In this approach, accident data is collected manually or processed using basic software tools to generate reports on daily, monthly, or yearly trends. While these reports are useful for understanding past accident patterns, they do not support real monitoring or future accident predictions, particularly during peak traffic hours when risks are highest. Moreover, the existing system does not effectively consider time dependent factors such as rush hours traffic, seasonal variations, or specific events that greatly impact accident frequency. It also struggles to manage large and continuously increasing volumes of traffic data. Due to the absence of predictive and automated capabilities, traffic authorities are forced to take reactive measures rather than preventing actions. This leads to delayed response, ineffective use of resources, and a higher likelihood of accidents during peak hours. Coming to this proposed system or base paper work, the proposed system focuses on predicting traffic accidents in advance by using time series forecasting techniques, especially during peak traffic hours. It begins with a systematic collection of historical traffic accident data, which is then cleaned and organized to remove errors and inconsistencies. By analyzing time based features such as Hartley intervals, daily trends, and seasonal patterns, the system gains a clear understanding of how accident occurrence vary during peak hours. To achieve accurate predictions, advanced forecasting models such as Arrhemia, S-Arrhemia, LSTM, and Profit are employed, allowing the system to capture both linear and complex nonlinear relationship in the data. The system produced both short-term and long-term forecasts, which are displayed using visual graphs and analytical reports for better interruption. These predictive insights help traffic authorities identify high-risk periods, plan preventive measures, optimize traffic control strategies, and allocate emergency resource proactively. Overall, the proposed system supports informed decision making, helps reduce accident rates, and contributes to the development of intelligent and safer transportation systems. Coming to the data set, The dataset consists of historical traffic accident records collected to support the analysis and prediction of road accidents using data-driven techniques. The accident prediction dataset is available on Kaggle, includes various attributes related to time, location, road condition, and environmental factors, which helps in understanding accident patterns. Features such as the date and time of the accident are used to identify peak traffic hours and temporal trends, while location related details enable spatial analysis of accident prone areas. Environmental attributes like weather conditions, road surface status, and lighting provide insights into external factors influencing accident occurrence. In some records, traffic related information such as vehicle involvement, road type, or accident severity is also included and can serve a target variables for prediction models. Overall, the dataset is well suited for exploratory data analysis, time series forecasting, and machine learning based accident prediction to identify high risk periods and support intelligent traffic safety planning. Coming to the novelty or extension or enhancement or improvement. The extension points highlights the additional improvements and enhancements made beyond the base implementation. As an extension, an LSTM forecasting model was implemented to better capture complex temporal dependencies in traffic accident data, and its performance was compared with the previously proposed models. The results showed that the LSTM model achieved higher prediction accuracy, demonstrating its effectiveness for time series forecasting tasks. In addition, explainable AI techniques such as LIME and SHAP were applied to interpret the model predictions by identifying the most influential feature values, thereby improving transparency and trust in the system. Furthermore, the Flask framework was used to develop a user-friendly web interface that allows users to input relevant feature values and receive accident forecasts generated by trained models, making the system more accessible and practical for real-world usage. Coming to the flow of the work, first, we need to import the required packages. This module involves importing essential Python libraries such as NumPy, Pandas, Matplotlib, Seaborn, Scikit-learn, stat models, TensorFlow or Keras, and explainable AI libraries. These packages support data processing, visualization, modeling, evaluation, and explainability. Next, load the traffic accident dataset. In this step, the traffic accident dataset is loaded from its source into the system using data handling libraries. The dataset is converted into a structured format for further analysis and processing. Next, data pre-processing. This module cleans and prepares the data to ensure quality and consistency. Null values are removed to avoid errors in modeling. Duplicate records are eliminated to prevent biased results, and the index is reset for proper data alignment. Categorical and numerical columns are identified to apply appropriate pre-processing techniques. Next, exploratory data analysis. EDA is performed to understand the dataset characteristics and underlying patterns. Summary statistics provide insights into the data distribution, while visualizations such as histograms and bar plot help analysis, accident counts, peak hour trends, and location-wise distributions. A correlation heat map is used to identify relationship between the features. Next, feature engineering. This module transforms raw data into meaningful impact features for the models. One hot encoding is applied to categorical variables such as peak hours categories and location types. A final feature list is created to ensure all relevant variables are included for model training. Next, train test split. The dataset is divided into training and testing sets based on unique intersections, with 80% of data used for training and 20% for testing. This approach helps avoid data leakage and ensures reliable model evaluation. Next, modeling. multiple predictive models are implemented to compare performance. This includes the negative binomial model for count-based accident data, SARMAX for time series forecasting with external variables, and MLP neural network for capturing non-linear patterns, and an LSTM model for learning long short-term temporal dependencies using lag features. Next, predictions. Each trained model generates accident predictions on the test data. For neural network models like MLP and LSTM, predictions are repeated multiple times, and the mean value is used to improve stability and reduce randomness. Next, evaluation. Model performance is evaluated using standard error metrics such as mean error, mean absolute error, root mean square error, mean absolute percentage error, and mean absolute scaled error. The results are compared numerically and visually to identify the best performing model. Next, we have save the model. The trained model are saved to disk for future use. This enables model reuse without retraining and supports deployment in real-time forecasting applications. Next, explainability. Explainable AI techniques are applied to interpret model predictions. Line is used to explain individual predictions for the negative binomial and MLP models, while SHAP provides global and local feature importance through summary and force plots, enhancing transparency and trust. Coming to the front end is developed using Flask framework, including user registration and login functionality, supported by an SQLite database to ensure secure access. Users can provide input data either as individual feature values or by uploading a CSV file containing multiple records for prediction. The input data is pre-processed using the same steps applied during model training to maintain consistency. The trained model is then used to generate accident forecast. The final prediction results are displayed to the user interface in a clear and user-friendly format, allowing users to easily interact accident risk or forecast. The algorithms used are negative binomial, SARMAX, MLP, and LSTM. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements are application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap. To execute the project, first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. IPYNB file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the project execution. Firstly, you need to copy the path of the code folder from the address bar of the file explorer and then open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Now, copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. The homepage of the project should now be displayed in the browser. This is a front-end built using the Flask framework. In this page, we have home button and sign up button. Now, click on sign up button so that the logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and the login HTML will be opened, where we need to access the application by username and a password. Then click on sign in so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and sign out button. Firstly, click on prediction button so that the single prediction and the bulk prediction modules will be opened. Then click on single prediction so that the forecasting peak hours traffic accident probability form will be opened, where you need to enter the details and generate a time series forecast predicting the likelihood of traffic accidents during peak hours based on historical patterns and current conditions will be opened. Now, let us enter the input values. The peak hour period value will be MP1. Location will be south. Major ADT value will be 1260. Minor ADT value will be 228. Number of legs value will be 4. Single heads will be 1. Horizon unit will be for hours. Horizon value will be like 2. Then click on generate forecast so that the input values are pre-processed and the output will be displayed as the given input parameters are printed here and the forecasting horizon is of 12 hours. And we also have the time series forecasting results by using different models. And next we have new prediction and view graphs. So as we have seen for single prediction, now let us check the input values for bulk prediction. When you click on bulk prediction, the CSV file uploadation form will be opened where you need to choose the file from the project code folder. Open test cases, test.csv file, then click on open so that the CSV file is loaded. And now let us give the values for forecast horizon. It's for hour and the value will be like 2. Now click on forecast from CSV so that the input values are pre-processed and the output will be displayed as CSV batch forecast summary. The total recorded processed is 102. Forecast horizon is 12 hours. The output file, we can download the file which we have uploaded in the CSV format is given here. And we also have the batch forecast results. Then click on new prediction so that again the forecast for bulk predictions will be opened where you can give the CSV file. And now click on view graphs so that the graphical representation of the project will be opened. So now let us check one by one. First we have distribution of accident count graph. This histogram with a density curve represents the distribution of accident counts across the data set. The distribution is right squeaked with most observations concentrated at lower accident counts and fewer instances of high accident numbers. This pattern suggests that while severe accident clusters are less frequent, they still occurs and must be considered in modeling. The distribution supports the use of count-based and time series models suitable for squeak data. Next, we have average number of accidents by peak hour graph. This bar chart illustrates the average number of accidents across different peak hours categories, including morning peak, afternoon peak, and evening peak periods. The results indicates that evening peak hours, particularly the later evening period, experience the highest average accident counts. This trend reflects increased traffic congestion, reduced visibility, and driver fatigue during evening hours, highlighting the importance of forced traffic management during these periods. Next, we have accident distribution by location zone graph. The box plot shows the distribution of accident counts across different location zones such as south, west, north, downtown, and east. Downtown areas exhibit higher variability and a greater number of extreme accident values, indicating increased risk due to density traffic and complex road conditions. Other zones shows comparatively low, medium, and narrow distributions. This analysis demonstrates how accident frequency varies geographically and emphasizes the impact of urban density and accident occurrence. Next, we have top 10 intersections by average number of accident graph. This bar chart displays the top 10 intersections ranked by their average number of accidents. It highlights specific intersections that consistently experience higher accident rates compared to others. These intersections represent critical traffic hotspots where safety interventions, traffic control measures, or infrastructure improvements may be required. The visualization helps prioritize localizations for targeted accident prevention strategies. Next, we have Pearson correlation matrix graph. This Pearson correlation matrix illustrates the linear relationship between the numerical and encoded categorical variables in the dataset. The target variable number of accidents shown a moderative positive correlation with traffic related attributes such as major and minor road traffic volumes, indicating that higher traffic flows in associated with increased accident occurrence. Peak hour variable shows weak to moderate negative correlations with each other during the one hot encoding, while location variables also display negative correlations among themselves, which is expected. Overall, the matrix helps identify influential features and confirms the absence of strong multi-collinearity. And next we have model performance comparison graph. The model performance comparison chart evaluates the predictive accuracy of four models: negative binomial, S array max, MLP, and LSTM. Using metrics such as ME, MAE, RMSE, MAPE, and MASE. The neural network based model, particularly MLP and LSTM, demonstrate low error values across most metrics compared to traditional statistical models. This indicates their superior ability to capture non-linear and temporal patterns in traffic accident data. Overall, the comparison confirms the effectiveness of advanced machine learning and deep learning for peak hour traffic accident forecasting. Next, we have line explanation for MLP model test index 0 graph. The line visualization explains the MLP model prediction for another individual test in SAINS. Index 0. The chart shows how specific feature values such as signal head conditions, traffic demand variables, peak hour indicators, and location categories either positively or negatively affect the model output. The variations in important features compared to the previous instance highlight that accident predictions are context dependent and influenced by localized traffic and temporal conditions, reinforcing the need of explainable AI in traffic forecasting system. Next, we have line explanation for MLP model text index 10 graph. This graph represents the local line explanation for MLP model predicting corresponding to text index of 10. It highlights the most influential features that contributes to the prediction accident count for this specific case. Features shown in green indicating a positive contribution towards increasing the prediction, while red bars represents features that decreases the predictive values. Variable related to traffic conditions, peak hour indicates, and location zones significantly influence the prediction. demonstrating how different factors interact at the individual levels. Next, we have line explanation for MLP model test index 20 graph. This line plot explains an individual prediction made by a multi-layer perceptron model compared to NB model. The MLP shows a different balance of inferential features. The strong positive contribution comes from WD-ADT MAGE is greater than 0.54%, while several features such as a sick head, no leg, and certain hours and location indicates contributes negatively. Overall, the graph illustrates how the MLP relies on both traffic-related and contextual features to arrive at its prediction, emphasizing the model's nonlinear decision behavior at a local level. And next, we have line explanation for Navy bias model text index 0. This bar chart represents a local explanation for line for a Navy bias model prediction on a single test instance. Green bar represent features that push the prediction towards the predicted class, while the red bars push it away. Features such as location indicates and hour-related variables have strong positive contributions, whereas variables like SIGHEAD, WD, ADT minimum, and specific hour features negatively influence the prediction. The chart highlights which conditions most strongly shape this particular Navy bias decision. And finally, we have explainable AI SHAP dependency plot for no-leg graph. This graph shows how the feature no-leg influence the model predictions using SHAP values. Each point represents an observation with the x-axis showing the value of no-leg and the y-axis showing its SHAP contribution. Positive SHAP value indicates that no-leg increase the model prediction while negative values decrease it. The color highlights interaction effectiveness of another features, suggesting that the impact of no leg on the predictive varies depends on recent lagged values. And then click on sign out. So finally, the project demonstrates that time series forecasting techniques can effectively predict traffic accident occurrence during peak hours by capturing temporal patterns and trends in historical data. Advanced models such as S-Aremia, MLP, and LSTM showed improved accuracy compared to traditional methods, highlighting their sustainability for complex traffic data. The integration of explainable AI techniques enhance model transparency, while the developed user interface supports practical deployment. Overall, the proposed system contributes to proactive traffic management and improved road safety by enabling time preventive actions. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.